Hey everybody. Last time we ended up talking about quantum signal processing, but we really didn't spend all that much time talking about ways in which it can be used. This lecture, we're going to rectify that by showing you how you can use the ideas of quantum signal processing in order to do optimal Hamiltonian simulation. So the key point here to generalize what we had before for quantum signal processing to Hamiltonian simulation is basically that what we can do is we can actually view a way of adding an extra qubit to our previous problem in order to be able to allow us to dilate a unitary that we're carrying out that has some trivial action on an eigenvector into a single qubit rotation on an extra ancillary qubit. This allows us to then do this, use this extra qubit to enact an eigenvalue transformation by transforming that single qubit rotation that we end up having on the auxiliary space. So to illustrate this, let's just jump into it. So I'll share my screen and load up this guy, add a new page. And all right, so to recall, what the whole idea of quantum signal processing was the following. What we have is we have an operation OX over here, which is a 2 by 2 matrix of the form square root x square root 1 minus x squared, square root 1 minus x squared, and x over here, which of course is equal to our y of 2 arc cosine of x. And again, this factor of 2 is because of the annoying double cover that we end up having for unitaries versus rotations. So in any case, this is what we end up having, and the quantum signal processing sequence ends up going as follows. Let u phi over here, where phi is a vector, be e to the I phi 0 z pi j equals 1 d O of x e to the I phi j z over here. This is our sequence. And the claim is there exists phi 0 through phi d such that u phi equals p of x negative square root 1 minus x squared q of x square root 1 minus x squared q star of x, p star of x, if and only if three conditions are met. 1, p and q are polynomials of degrees less than or equal to d and d minus 1, respectively. Second thing that we end up needing, let me just close this stuff down so I don't run into memory problems. Okay. There we go. All right. The second thing that we end up getting is that p and q are polynomials of degree d and d minus 1. If p is even, q is odd, and vice versa. Then, and the final one, 3, is that the absolute value of p squared plus absolute value of q squared times 1 minus x squared equals 1. And this is a trivial constraint from unitarity. So these are the conditions that we have for doing it. So if you know the p and q pair that you want to find with this is actually really straightforward. One of the challenges here is that if you don't know the q that you end up needing for a fixed p, then it's a little bit more difficult to be able to actually build a polynomial for dealing with this. And there's other algorithms that you can end up seeing. There's a great paper by Jungwang Ha that ends up showing you how you can actually end up computing these things. There's also work by Lin Lin, work by Isaac Schwang and his students, as well as others that end up giving you more efficient ways of finding the Q if you only know the P that you're looking for. But for the moment, let's just assume that we have P and Q pair that end up satisfying all of these requirements. So that's what we can end up doing. But the key point here is that this is always going to end up yielding a 2x2 matrix. How can we end up taking a more complicated problem and recasting it inside this language? Well, here's a way. This hint is given by qubitization. So qubitization, the way that it's being used now is a little bit different than I think Guanghao Lo, who was the inventor along with Isaac Schwang of this technique, probably intended for it. The basic idea, I think, of what qubitization was intended to mean was the following. Imagine what we have is we have some unitary. Let W be a unitary such that W acting on lambda j equals e to the I lambda j lambda j. So it's just an eigenvector of the unitary matrix W. So if we construct this, then the question is, what would happen if I built a circuit that for fixed lambda j coming in over here, we'll just apply a controlled W? Well, this circuit is actually pretty kind of straightforward to think about. We can say that this is equivalent to 0, 0 tensor identity plus 1, 1 tensor W acting on identity tensor lambda j. So here I'm kind of using block encoding notation in a way in order to be able to make it so that I'm only partially evaluating the unitary transformation on the lambda j. So if we use this, then what we end up getting is we end up getting that this will give me 0, 0 tensor lambda j plus 1, 1 tensor e to the I lambda j. But phases are associative. This is equal to the following. It's equal to 1, 0, 0 e to the I lambda j. If you're using quantum jargon, people will call this the phase kickback effect. But this is equivalent to I tensor lambda j times identity acting on the lambda j times I tensor lambda j. Okay, so this means that this is equivalent to RZ of lambda j tensor identity acting on identity tensor lambda j. So by controlling our W operation here, which is an arbitrary unitary, acting on an eigenvector, this allows us to implement a Z rotation. So now what we've done here is we've got a single qubit, and we've converted our action on this multi-qubit space into one that's just impacting this single qubit space up above. Now, once we have it in this form, we can manipulate it. So to make it a little bit more clear how we can do this, well, let's change our circuit up in the following way. If we put an S gate in here, where recall that S is sorry, not 0, it's that. Then we do a Hadamard transform, and we do a W Hadamard transform, and then an S dagger over here. Then the result that we end up getting out of this, acting on the state lambda, this will end up giving us, just by basis transforming the RZ, this will end up giving us a rotation about Y through an angle of lambda J, tensor identity, acting on identity tensor at lambda J. Cool. So this gives you a way of writing this as a particular matrix. And just to put it into perspective about what this would boil down to, if we computed these elements here, this would be cosine of lambda j over 2 minus sine lambda j over 2 sine lambda j over 2 cosine lambda j over 2. So using our previous language that we used for quantum signal processing, this actually corresponds to O of cosine lambda j over 2. Okay, so you can see here that we have the exact same form that we were using up here for our quantum signal processing sequences. So if we wanted to be able to convert this operation that we have over here to one that has a different eigenvalue, well, we can do that just by manipulating this top qubit. For example, let's say that I had a state over here that is, I'll call this a state of plus y. And plus y has the property that poly y operation acting on plus y is equal to just plus y. Okay. So if this is the individual eigenvalue that we end up having for it, then we would end up having that O of cosine lambda j divided by 2 acting here, acting on plus y. This is just going to be equal to e to the I lambda over 2 times plus y. Okay, so these are our eigenvalues, or I say lambda j over 2. These are our eigenvalues that we end up having over here. So we have now a exponential of our original eigenvalues kicked back over here. So if, for example, I ended up transforming this to some polynomial of cosine lambda j divided by 2, then you can see that what we have over here is we have an operator whose eigenvalues are now going to be a polynomial function of the original ones coming in. So this allows us to be able to do an eigenvalue transformation on a particular object. So once we've added an extra qubit, the eigenvalues of the larger system can be transformed using QSP. All right. And so that's the basic idea behind it. And so to give an example of how we can use this is, let's consider an application to Hamiltonian simulation. So Hamiltonian simulation is something that I've talked about quite a bit in previous lectures, but let me just remind you of how Hamiltonian simulation ends up working. With Hamiltonian simulation, what we have is we want to build a unitary u of t such that the unitary u of t satisfies the following operator differential equation, where H over here, this is not the Hadamard gate, this is a Hamiltonian matrix. And so Hamiltonian matrix really is just physics jargon for this being a Hermitian operation. Okay. Now the solution to this differential equation can be seen. First, you can see it by doing a series expansion and verifying that this series expansion satisfies it. But the solution in general to this is u of t equals e to the minus I h t. Okay, so the task is then to end up building this guy over here. And note, because h is Hermitian, it has real eigenvalues. This implies that the eigenvalues of e to the minus I h t are of the form e to the negative I lambda j t, or lambda j in real. And this implies that the absolute value of the eigenvalues of e to the minus I lambda j t equals 1. And this implies that e to the negative I h t is unitary. Okay, so this means that this is a unitary matrix that we can look at building in our quantum computers. And just to give you an idea about why this is important, many quantum algorithms end up boiling down to this, like generic differential equation solvers using linear combination of Hamiltonian simulations, which is a recently developed idea by Lin Lin, his students, and Andrew Childs, ends up reducing the problem of solving a differential equation to linear combinations of these guys over here. So using LCU on different examples of these. It was used in the original Harrow, Hasselbalch, and Lloyd algorithm. And also, it's used in simulating molecular and atomic systems because they are basically just exactly this same form. The Hamiltonian is just a series of interactions that you end up describing between individual electrons. But at the end of the day, ultimately, the main task on a quantum computer is to build the exponential of this guy for some Hamiltonian that describes a system. And yeah, so that's what we want to do. But the question is, how do we load the Hamiltonian matrix into a quantum computer? The way that we're going to assume that we're doing it is using a linear combination of unitaries, block encoding for it. So the idea is we're going to assume, without loss of generality, that the Hamiltonian is sum over j, alpha j, uj, for alpha j greater than or equal to 0, and uj unitary, such that we have a oracle prep acting on 0, which is going to give us sum over j alpha alpha, or sorry, j, divided by our normalization constant, which I'll call root alpha. And then we'll have a select operation, which when given a register that's of the form j and acting on some arbitrary quantum state over here, we'll just select the jth unitary and apply it to our quantum state. So now, given these operations, what we want to do is we want to build a operator W, which is defined to be negative select prep, sorry, identity minus 2 prep 0, 0 prep dagger tensor identity. Now, I'll often drop this extra identity in here because it's clear that the preparation circuit is acting on the ancilla register up at the front rather than the main register below. But I just wanted to remind y'all that there actually is a extra Hilbert space that this prep only acts trivially on. So what's happening here? High level, what this is doing is this is creating following sort of setup. We have our select operation, but interspersed now with these reflections over here. And this actually will look really reminiscent to the LCU lemma, where LCU would end up saying that if we applied prep select prep dagger over here, then we'll construct a unitary that is of the form h over alpha question marks everywhere else. So this will end up block encoding the Hamiltonian. But what we want to do is we want to do something kind of a little bit different here. What we'd like to do is we'd like to block encode this as a kind of rotation or a phase that we end up kicking back. So let me just show you exactly how that's all done here. W is a slightly permuted version of this with a reflection instead of just prep sandwiching about it. And W will end up having the following action. So first off, the claim let h acting on lambda j equals lambda j, i.e. let lambda j now be an eigenvector of the Hamiltonian matrix that we would like to simulate. So if h has the following action, then my claim is the vector alpha lambda j, which is just equal to prep 0 lambda j. Now I apologize for this notation. Alpha over here I'm using basically just as shorthand for prep 0 because of the fact I'm going to be writing so many prep zeros down below that it's useful just to kind of have a slightly abbreviated notation for it. So I apologize for for having to introduce this, but that's what this is the notation we're going to use. So this state and a state phi tilde j form a irreducible 2D subspace such that W will map the span of these two vectors to itself. Okay, so what am I saying over here? That basically what will happen is these two vectors over here, when W acts on those two vectors, we'll have space corresponding to them. We'll have an individual vector coming out here. Let's call this vector V. All W will end up doing inside this two-dimensional space is it'll just end up mapping V to a rotated version of V. So if this angle was theta over here, then we'll get some angle phi coming back out for V prime equals WV. So basically, what ends up happening here is that in order to understand the action of W, we only need to really understand a two-dimensional space here. And that's the space spanned by this eigenvector tagged with this extra junk and this remaining vector, phi j perp over here. Now, based on this hypothesis that it's a 2D subspace, what we can do is we can end up finding the second component by Gram-Schmidt orthogonalization. So in particular, we can end up taking, based on this hypothesis, that phi j perp is just going to be equal to W acting on alpha lambda j minus the projection of this divided through by some normalization condition. Okay, so these two vectors are clearly orthogonal because if we take the inner product between phi j perp and alpha lambda j, then the inner product here will cancel the inner product there. So these two vectors are at least orthonormal, but it isn't necessarily obvious that W will actually end up forming a irreducible two-dimensional subspace that have both of these vectors in it. So in order to see that, let's actually just go through and compute the matrix elements. My claim is then, inside this subspace, what we can do is we can end up representing W as a following matrix. We can represent it as alpha, lambda j, W, alpha, lambda j. And then here, we'll end up having alpha, lambda j over here times W phi perp. And then down here, we'll have phi perp. Now W alpha lambda j. And we'll have phi perp, W phi perp. I guess there's a j's here. Okay. This is the action of W on this irreducible two-dimensional space. Now, question you might have is, hey, haven't you put the cart before the horse here? You said that we're hypothesizing that this is a two-dimensional space, but what if it isn't? Well, there's an easy way to check. All that we need to be able to do to check is be able to ensure that every row and column of this matrix ends up forming a unit vector. If it forms a unit vector, then because of the fact that we know W is unitary, since it's a product of unitaries, then the result has to end up being only two-dimensional because 100% of the support is found inside a two-dimensional space. So that's what we're going to do. We're going to show that the rows and the columns of this 2D matrix are unit vectors. Then that's it. We're done. So I'll show you two of the matrix elements here, the two easy ones. The rest of them can be found using a little bit more cumbersome algebra, but it's not so bad. So let's take a look at the first element, case 1. Let's find alpha, lambda j, W, alpha, lambda j over here. Okay, well, expanding this out, I can write this as 0, lambda j, prep dagger, just because this is equal to 0, prep dagger by definition. Then we have W, which is just select times identity minus 2 rep 0, 0, rep dagger acting on prep 0 lambda j. Those two terms kill each other. And we end up getting then that the action of the reflection operator, oh, sorry, there's a minus sign here. The action of the reflection operator here on 0 then will end up giving us just a minus 1. So what this will end up giving us, once we simplify it, is it'll give us 0, lambda j, grep dagger, select, grep, lambda j, 0. Oh, sorry, I screwed up my orderings of terms. It is 0, lambda j. There we go. Now, this, using the LCU lemma, it actually ends up just being 0, or sorry, lambda j h over alpha lambda j, because, as I mentioned before, this combination of prep, select, prep, dagger is just equal to hj over alpha. And since we're only interested in this block, because of the 0, 0 projector here and here, then it just becomes h over alpha. So this is just equal to lambda j divided by alpha. Cool. All right. So LCU ends up giving us that matrix element is lambda j over alpha. And this allows us to actually also simplify our expression for phi j perp, which, if you recall, was equal to W acting on alpha lambda j minus alpha lambda j times this matrix element, lambda j h over alpha lambda j, divided by some normalization condition. All right, now this over here, we can now substitute in, and we can see that this is just equal to W minus lambda j over alpha acting on lambda j, divided through by norm. Therefore, we end up having that norm squared has to be equal to, sorry, there's an alpha here. It has to be equal to alpha lambda j times W dagger minus lambda j over alpha times W minus lambda j over alpha times alpha lambda j. Cool. So cross multiplying, what we end up getting is we end up getting that this is equal to the 1 plus lambda j squared over alpha squared minus 2 alpha. Okay, fine. Let me not skip that step. Lambda j w alpha lambda j minus alpha lambda j w alpha lambda j. But recall that this over here is real valued. Because this is real valued, then these two terms have to be equal to each other, and further have to be equal to lambda j squared divided by alpha squared. So therefore, the normalization factor squared that we end up having in this expression is of the form 1 minus lambda j squared over alpha squared. And so from this, we can end up seeing that phi j perp is equal to W minus lambda j over alpha, acting on alpha lambda j divided through by square root of 1 minus lambda j squared divided by alpha squared. Okay, wonderful. So now we have an explicit expression for phi j perp using this matrix element that we computed. So we're going to use that in order to be able to compute our second matrix element of this guy. We're going to use it to compute that matrix element down here. So computing that matrix element, we end up getting that phi j perp w alpha lambda j is equal to alpha lambda j times w per adjoint minus lambda j divided by alpha times w times alpha lambda j. All right, so this is actually easy. These two unitaries are going to kill each other when applied on it, and the remaining is just going to end up going through. Oh, and sorry, I forgot about the normalization factor, 1 minus lambda j squared over alpha squared. So this ends up giving us just simply 1 minus lambda j squared divided by alpha squared from the numerator divided by 1 minus lambda j squared divided by alpha squared from the denominator, which of course is equal to square root 1 minus lambda j squared over alpha squared. So if we combine these two results together, we end up getting that w then is equal to, from our first component, we argued that it's lambda j over alpha. This one down here is 1 minus lambda j squared divided by alpha squared. And here, the first thing to notice is that the first column in this is clearly a unit vector. So therefore, there's nothing else that we can potentially add to it. Going through and computing the rest of the matrix elements, I won't bore you with the algebra, but it's similar. We end up getting this is negative 1 minus lambda j squared over alpha squared and lambda j over alpha. We can see then that this matrix over here is a unit vector in this direction. It is a unit vector here. And further, we can end up seeing that the rows and the columns are orthogonal. This implies that W is unitary. Hence, W acts as a irreducible, acts on this 2D irreducible space, i.e. it doesn't like mix this. So another way of looking at this is that if we ended up having our initial vectors coming in here, then our initial vector eigenvectors will always lie inside an irreducible two-dimensional space that W will manipulate. So W kind of can end up looking like the following. It will end up looking like a series of direct sums of 2 by 2 blocks over here, where each of these will be spanned by alpha, phi j, and the phi j perp. So this would be, I guess, by 1, and this one, of course, will be alpha by 2, phi 2 perp, and so on and so forth. You get the idea. Now, the question is, what are the eigenvalues of this? Okay, the eigenvalues of W are actually really easy. We can see immediately that this is just Ry of arc cosine of lambda j over alpha. So if W is the arc cosine of this, then we can see that the eigenvalues are going to be E to the plus minus I arc cosine of lambda j divided by alpha. So these are actually very similar to the eigenvalues that we would ideally want. If we looked at e to the negative I h t, which is what we're interested in, we can write this in its eigenbasis as the following. We can write this as a sum over j, lambda j, e to the negative I, lambda j t. So you'll note that the biggest difference between the two is this factor of the normalization constant alpha in the denominator, normalizing it. There's no t here. There is a t there. And there's the, of course, arc cosine here and plus minus. So what do I mean by that? What I mean is that if we start with a initial vector coming into our system, let's say we have alpha, sum over j, let's put up some bj's here, times the expansion coefficients lambda j. And let's set this to be equal to alpha psi naught. Okay, so if this was our input state coming in here, then what we would end up having is we would have that this input state is actually going to be supported by both of these eigenvalues. I'm going to call these eigenvalues over here. Let's call them phi j plus and phi j minus, corresponding to the two different eigenvalues that we can have from it. So if that's what we end up getting, then we'll have that that w acting on one of these terms in the sum, alpha lambda j over here. This will be equal to some expansion coefficient, w, times, I don't know, let's call this beta, phi j plus, plus gamma phi j minus, or arbitrary expansion coefficients, beta and gamma. So if we express it in the eigenbasis, then what will end up happening is that an application of w will end up giving us beta e to the I arc cosine of lambda j over alpha phi j plus and plus gamma e to the minus I arc cosine of lambda j over alpha phi j minus. So what this ends up meaning, if we draw this in a kind of a 2D plane, is that the phase that we have on both of these components, let's say it started out being 50-50, these changes, these phases are going to end up actually causing the sign to change between these two values. And that will end up causing a rotation inside this 2D plane that we end up getting over here spanned by phi plus j and say phi minus j. Okay, so we'll get a rotation inside this because of the differences between the positive and negative eigenphases. And that's not what we want. What we would want is if we had, say there was no positive or negative eigenphase, then we would end up getting our W would evolve our state according to the correct evolution up to the arc cosine. So we'd like to not just remove the arc cosine from this, but we'd also like to remove the plus minus sign because of the fact that it causes these two eigenvectors in the support of our initial vector that we put in to start rotating apart from each other. So how are we going to do this? So we need to transform the eigenvalues of W to e to the negative I lambda j t. So we want to build a transformation that will transform both of these eigenvalues over here to the right thing. Okay, so the way that we're going to go about doing this is first, step one, we need to kind of qubitize using Guanghao's language. I should mention often in papers, using qubitization to perform a simulation often just ends up referring to taking the W operation, doing phase estimation, and taking the cosine of the result. But here I'm using it, I think, closer to what Guanghao might have intended with his original paper. So we qubitize here by doing the following. What we do is we say, okay, we add an extra qubit up to the top, and I'm going to define now my O of lambda j, I guess I'll call it, which will be equal to the circuit that I mentioned before. It'll be a S gate followed through by a Hadamard, followed through by a controlled version of W, followed by this over here, an S transposed. Now, and if this has lambda j, sorry, I guess a state of now phi j plus down here, then what this circuit is equivalent to is this circuit is equivalent to just phi j plus down here and our y of uh, 2 inverse lambda j over alpha. Okay, so that's what this whole thing is equivalent to. So the eigenvalues then that we have paired with phi plus can now be controlled by manipulating this rotation up here on the additional qubit. So in particular, if I ended up having, say, a plus y phi j plus, this whole thing will end up getting us mapped to now, by default, e to the I arc cosine of lambda j over alpha plus y phi j plus. And so if we manipulate this rotation up here to end up having a different eigenvalue, then I can use that in order to transform this eigenvalue. So in particular, what would I like to do? What I'd like to do is I'd like to be able to get our matrix up here, which in this basis ends up corresponding to the following. This will end up looking like lambda j over alpha, negative square root of 1 minus lambda j squared over alpha squared, square root 1 minus lambda j squared over alpha squared, lambda j over alpha. And we'd like to be able to transform this into something that has eigenvalues that are of the form e to the plus minus I, sorry, not plus minus I lambda j t for our value of t. So the way that we can end up doing this is just by first, let's do a change of basis to simplify everything. If we did a change of basis, we can express this as something like e to the negative I phi, sorry, our cosine of lambda j over alpha, the I cosine of lambda j over alpha in its eigenbasis. So in order for us to now do the transformation, what we'd like to do is we'd like to be able to use this amazing result known as the Jacobi-Anger expansion. Now, the Jacobi-Anger expansion was initially used in signal processing in order to be able to interconvert different types of waves into other types. And what we want to do with the Jacobi-Anger expansion specifically here is the Jacobi-Anger expansion states that e to the it cosine theta is equal to j0 of t plus the sum from n equals negative infinity to infinity of negative I to the n jn of t of e to the negative, yeah, sorry, e to the j theta over here. I. Oh, sorry, there's a j there. It's actually n here. Okay, so here, the jn correspond to the nth Bessel function. So the Bessel functions are a class of special or orthogonal polynomials that end up actually decaying really rapidly with n. These end up going like order e to the negative n. Okay, so they end up decreasing very rapidly as n ends up going to infinity. So in principle, you don't have to do too many terms in this expansion in order to be able to get it to converge. The next thing is by multiplying everything by an overall number of w's that we look at, we can approximate this as a finite sum by this being j0 of t plus e to the negative k I theta sum n equals 0 to k of negative I to the n j of negative k plus n. And I guess I should put a negative k plus n over here. And then this will just be e to the n theta I. Okay, so this gives us a cutoff for doing this. And the value of k, if we want the error to be epsilon, from the asymptotics of the Bessel function, which you can end up looking up on Wikipedia, you can end up seeing that the value of n that we end up needing in order to achieve this is order log, or I should say k, is order log 1 over epsilon divided by log 1 over epsilon. Okay, cool. So that is a truncated version of the Jacobi-Anger expansion. Now you might wonder, okay, well, why is it again that that's what we want to do? Well, if we have our matrix up at the top over here, where we have e to the negative I arc cosine of lambda j over alpha. And we have the same thing, e to the I, same junk over here in zeros. If we can perform a polynomial transformation on this guy and go to p of dot 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 0 0 down here, where this is p, then what we'll end up doing is we'll end up saying, okay, well, e to the negative I arc cosine of lambda j divided by alpha will end up going, and actually let's change this a little bit. I said t, let's make it alpha t in here. Then this will end up corresponding to, then, using the Jacobi-Anger expansion, this will be e to the negative I, oh, and I should put a minus sign here, negative I alpha t cosine of lambda of arc cosine of yeah, of arc cosine of lambda j divided by alpha, which is of course equal to e to the negative I lambda j t. Now, cool fact, if we did the same thing to the negative eigenvalue over here, then we'd have a minus sign in here. But because cosine is an even function, we get the same result. So this means that we can use the Jacobi-Anger expansion as our polynomial transformation that we would like to do after simple basis change to put it in this diagonal form. That will allow us to be able to manipulate it. Furthermore, the degree of the polynomial transformation that we end up needing is equal to k, which is order log 1 over epsilon divided by log 1 over epsilon here. And so that's one of the things that is kind of beautiful about this. And what we can do is when we put this all together, then the total number of queries that we end up needing in order to be able to do this. Oh, I'm sorry about that, actually. The degree k isn't just the truncation value that we end up needing to set. We also need to increase it by this alpha t parameter that we end up getting because of the first term that we have in here, this the alpha t stuff. So this ends up giving us a total number of OX needed that scales as big order alpha t plus log 1 over epsilon divided by log 1 over epsilon. And the way that this ended up working is by taking our Hamiltonian, converting that into a walk operator that in a higher dimensional space. Then, and we did this by putting an extra alpha register on it. Then we dilate it further and convert this into the controlled walk operator by adding an extra qubit to that. Then what we do is we apply QSP using the Jacobi-Anger polynomial. And this will end up giving us a new function. Let's call it QW, using the following number of operations at the top. And QW has the property that when QW acts on a state alpha lambda j over here, it will map us to alpha e to the negative I lambda j t lambda j. So, and I'll put also this extra qubit that's used for qubitization off in front. And so what this ends up meaning is this is equivalent to bilinearity, because it will do exactly the same thing to every possible input eigenstate that we put in. This is just exactly the same thing as e to the minus IHT acting on lambda j. So this is equivalent to e to the minus IHT. Okay, wonderful. And that's it. So this shows how we can add an extra qubit, go through a series of the dilations in order to be able to build a polynomial that ends up allowing us to transform a walk operator that is close to the ideal simulation, but has these defects like the arc cosine or the minus signs in places where we might not want it, and also these factors of alpha. We can put all of this together using an appropriate polynomial, and then just use QSP in order to be able to transform it all in the end. At cost, that I should note, scales linearly with time. And also, it ends up scaling, the extra logarithmic cost is additive, not multiplicative. And actually, this algorithm can be shown to be optimal. The optimality proof ends up following from proposing a Hamiltonian that can be used in order to compute the parity of a bit string. And then you can show from a polynomial lower bounds that the number of queries needed to do the simulation of the parity or the estimation of the parity has to be at most linear. And you can show that any improvement on the asymptotic scaling of this algorithm would allow us to violate that lower bound. And so therefore, the simulation method isn't just actually like a convenient way of performing simulation or a neat trick that we can do in order to fit Hamiltonian simulation into this paradigm. It's actually, in some sense, the best simulation method that you can possibly use if your problem doesn't have additional structure that you can take advantage of. So that's it. That's how you can use a polynomial transformation in order to be able to, through QSP, in order to be able to do something on many qubits. What we do is we use, again, a dilation in order to make that happen. Next time, what we're going to do is we're going to use the exact same sorts of methodologies in order to be able to tackle the problem of fixed point amplitude amplification, where what we aim to do is come up with a form of Grover search that doesn't over-rotate, that'll actually end up sticking around the target that we would like to get to without us needing to know what the success probability is. Thanks a lot. Hope to see you next time.